let's get started with this week's content. Can I have each side of the table please grab a whiteboard? I will not be lecturing today, but I will just briefly list out a few equations.
Yeah, all right.
Momentum is a vector quantity that is kind of hard to put your finger on. It's not something that you would normally feel like a force or see like motion, but it's very useful mathematical lens to view physics problems through. Momentum is a vector quantity that just has mass times velocity. Since it's a vector, it can be positive or negative. It can point to the left or it can point to the right. Impulse is another idea that describes the change in momentum. Delta P equals F net force times delta T, which basically says that if I push on an object with a force over some amount of time, its momentum will change. The longer that I push on it and the harder that I push on it, the more its momentum will change. And we will deal with the idea of impulse, thinking about it being the area under a curve for a force versus time plot. We'll deal with that in the second half of class today. The reason why momentum is useful is because we can apply momentum conservation, much like energy conservation, where the total amount of momentum in the beginning will be equal to the total amount of momentum in the end. And for our first half of class, we're going to talk about two-body systems, where we have two objects colliding with each other and transferring momentum. So we will be working as tables for the first half of class, where we have one red car with its own mass and its own initial velocity, and that red car will change its velocity after a collision. So it will have a new final velocity. And then we will also have a blue car that has its own mass and its own velocity before the collision, and its own mass and its own velocity after the collision. We're going to gain practice working on our momentum diagrams here in just a moment. So this will be a great opportunity for us to practice. We have 4 different situations that we're going to try drawing these for. And now it's time for us to wake up our computers and do a little bit of capstone work. So we actually only need one person at each table to connect up. So maybe decide which person at the table is going to do the capstone work. Maybe whoever's feeling more confident with the computer for right now. Go ahead and open up Capstone. Turn on your 2 cars and go to the sensor data. And get them both connected.
Yeah, you got to use
Sorry guys, laughing. 75170 in a thread.
Next one is 272014. Right.
75170 in a thread.
I'm getting connected up. All right. Now, please carefully pay attention to the experiment that we'll be doing as our warm-up activity. We're going to start off with the simplest possible type of collision that we can model. What's that?
It's just not coming up.
Nate, can you go help connect up some cars, please? I think some of them might be a little low on batteries, too. So let's see how they can connect. So what we're going to do is we are going to model an inelastic collision. Inelastic collisions are where momentum is transferred and 2 objects stick together. So the first one that we're going to think about is what happens when we have the red car coming in with some speed and the blue car not moving at all. It's going to think about how fast it's moving, what its mass is, how fast it's moving, what its mass is, before and after the collision. Okay? That's the basic experiment that we are going to do. Before we get started with that, though, we will have to do a couple of things. figure out what way you want. We're going to make all of your cars move toward the computer. How about that? So we will call toward the computer the positive direction. Get your cars on the track so that their Velcro edges are facing each other. And one of your cars should be pointing with positive X toward the computer. And one of your cars should be backwards. Determine which car is backwards. Which one is not pointing its positive X in the right direction. For me, it's the red one. My red one is not pointing positive X that way. It says positive X is going that way. So I need to go into the Smart Car Position Sensor and click on its properties and change the sign. So, for the red car, for me, go to Smart Car Position Sensor, go to Properties, and then go to Change Sign. And then when you're good, go ahead and hit OK. Now we can close this, and we do need to do one other thing before we get started. We need to zero out all of our sensors. So please go down to the bottom there. Find your Smart Car Position Sensor for your red car, and then hit the Zero Sensor button. Zero Sensor now. Make sure it's not moving, nobody's touching it. Then go to the Smart Car Position Sensor. I'll slow down a bit. Nate? Smart Car Position Sensor down at the bottom.
No, I got it.
Position Sensor red should be zeroed. And then Smart Car Position Sensor blue. And hit 0 again. So both sensors should be zeroed. Red and blue should be zeroed out. Red should be backwards, or one of them should be backwards in terms of its sign. And then at the bottom, click this and go to Common Rate. What that means is it's going to collect both of these at the same time. So at the bottom, make sure that you have Common Rate selected and keep it at 20 Hertz for now. That will work. We're going to model the momentum for each of the cars before and after the collision, so we'll need to know something about their mass and their velocity. Before we figure out the mass, I want us to add a plot area to our graphs by selecting that one right there. And I want velocity of one of the cars. So go find Smart Car Position Sensor, make it velocity for one of your cars, red, and then make the bottom one velocity of blue. You can see that I have velocity of my red car on the top, velocity of my blue car on the bottom. Doesn't really matter what order they're in, but you do need to have the two separate graphs of velocity versus time. Get this out of the way real quick. And then the experiment that we're going to do is we are going to end up, my track's a little smaller, we're going to hit record, wait for it to get going, we're going to send the red one in, and then after the collision they will have some velocity. So here you can see this was the velocity before the collision. I'll auto scale so we can see it a little closer. This was the velocity before the collision for my red and my blue car, and this was the velocity after my collision for the red and the blue car. I'm going to add a multi-coordinate tool so that I can see what those velocities were. And right at that little hump, that downfall right there, that's where the collision actually happened. That's where they collided and transferred some momentum to each other. So we're going to use this tool to figure out what our velocity was before and after the collision. For me, on our whiteboard soon, on one side of the whiteboard, I want you to put V1 initial for the red car, mine's 0.443 meters per second. I will put V1 final in a moment. And for my blue car, you will want to have V2 initial and V2 final on there. My initial blue velocity was 0 meters per second. And you want to try to get this multi-coordinate tool, you want to gather the data like right before the collision. That means I don't want you to just gather it like kind of far away from the collision, because you'll notice that this is actually sort of sloping down because of friction. So you want it like right before the collision, and then we want to get the velocity right after the collision. One more to the left. Let me just look at my number real quick, sure. So after the collision, mine are moving at 0.213 meters per second in this situation, and 0.213 meters per second. On your whiteboard, on one whiteboard, I want to have the mass of your first car, and the mass of your second car, and the velocities before and after the collision. From there, you will calculate P1 initial, P1 final, P2 initial, and P2 final. Maybe while someone is collecting data, you could have two people calculating, one for the red, one for the blue. And so on one side of the table, we're going to do the calculations, and on the other side of the table, we're going to set up a momentum diagram, and we're going to try drawing those out, getting some practice. Okay, I think we're ready to start collecting some data. I'll walk you through some stuff in a little bit, but let's just get one good data run, see if you can get these numbers on your board, and then I'll talk about how to do the momentum diagram as well. Let's go. So now for the people who are drawing the momentum diagrams, these are the rectangles that we talked about in the PowerPoint slides. This is a really simple momentum diagram. It's actually the same one from the PowerPoint slides. That's what we're going to warm up with. Your first rectangle should have a width that is representative of the mass. So my first mass is 0.275. So that width should be about just some arbitrary length. Maybe I'll say 10 centimeters. And the other mass is the same, so it needs to be the same length, M2, 0.275 kilograms. I'll only help you with the first one. The next ones we'll do separately, and you'll have different examples. So since they both have the same mass, they both have the same width of rectangle. And then you need to draw the height of the rectangle that is at the velocity value that you had initially. So my initial velocity was 0.443, 0.443 meters per second. And I will draw my red rectangle like so. Make sure that you draw them side by side. My second rectangle has a height of 0 at first. So this is just a flat rectangle with no height at all. And then after the collision, I should still have the same mass, so I should have the same width. M1, 0.275 kilograms. M2, same. M2, 0.275 kg. And now they do have a new velocity, so their height should be lesser. In fact, in this case, my height should be about half as much as what it was. Thank you, Nate. And so I draw this rectangle at about half the height. There. And the other blue rectangle will also be at the same height because they stuck together. They have the same velocity. There. And then we can calculate what the final velocity is by doing M2 V2 final. I want you to actually calculate a number by figuring out what that area is of that rectangle using the numbers that you have from your calculation board. So this gives something for the other people to do on the other side of the table as well. So let's get it going.
Alright, so what was our M1?
Good correction, thank you. Very nice thinking on the fly, that's right. Since we had kilograms for mass and meters per second for velocity, we multiply those together, and momentum doesn't have special units, but it does have kilograms times meter per second. So you got to make sure that you label that on all of your boards in the future. And now it's time for us to try a more complicated situation. So please take down your whiteboards, erase them. I'll erase mine in just a moment. And please follow me for this one. Nate should have distributed some different masses for you to put on your cars. So now what we will have is we're going to still do the same situation where the second one's not moving, the first one comes in, but the masses are different. And this will end up making it not look so nice and easy like it did there. It's going to change the width of your rectangles, and it will change up the way the velocity ends up being distributed. So we're still going to do the same experiment of red comes in and sticks to blue, and you gather the data the same way that you just did, but I want us to switch the responsibilities of which side does which. So if your side calculated this time, you got to draw, and if your side drew last time, you got to calculate. All right?
She does not have an attitude.
All
We
right.
make it clear you don't like
We're
it.
going to move on to the next example. I really think that one worth looking at is this group's momentum diagram, which they really had a pretty cool difference. They didn't put, they said is it would be okay if we just put all of our masses on one of them. We think that would be more fun and more interesting. So you'll see that their green rectangle is very wide, a very large mass, and their orange rectangle is not as wide because it doesn't have as much mass. And it started off with a very high velocity, and when they stuck together, ended with a much lower velocity. So that's a very interesting little result there. It really shows the difference more clearly. So the next scenario that we are going to look at is another inelastic collision, but this time both will be moving toward each other. Okay, we don't need to change anything on capstone, but we are going to send maybe one in sort of slowish and one in sort of mediumish. So I'll go slow with blue, medium with red. And that is the collision that I want us to measure, calculate, and draw the diagram for. Again, if you were on one side of the classroom, or one side of the table, you will, if you drew the diagram last time, now you're calculating. If you calculated last time, now you draw the diagram. I sense that there are some questions. Lillian? That's correct. The velocity for one is negative, and you must draw it below on the diagram. Jason? Nope, let's stick with the same masses also to keep it interesting and spicy.
Zero it out again.
Okay, looks like most of us have it. Pretty nice. We're going to do one more scenario before we take our break. We got good timing for today. So the last situation that we are going to do is we are going to do an elastic collision. So what we'll do for this one is we will just reverse the way that these are pointing. And now you'll see that there is a magnetic bumper on each end. If you've ever played with magnets, you know it's pretty hard to make them actually touch. They push off of each other. And so this will model an elastic collision. Inelastic means the objects stick together. Actually, that's technically a perfectly inelastic collision. And if it's just an elastic collision, then that means that some energy is lost. But in an elastic collision, the kinetic energy will be conserved and the momentum will be conserved. So I need you to also calculate one additional thing if you're one of the calculator people for this one. I'll come to you in a sec, Jason.
Yeah.
I want you to calculate the initial kinetic energy for the first object. I want you to calculate the initial kinetic energy for the second object. I want you to calculate the final kinetic energy for the first object. And I want you to calculate the final kinetic energy for the second object as well. So since these objects are moving, they're not changing their height, there's no spring. The only energy that we have here is kinetic energy. And in an elastic collision, these should have the same kinetic energy total in the beginning and the end. Jason, you had a question.
Will we have to reverse the signs in the computer?
That's a really insightful question, but actually we don't. We're just going to pretend like, really we're going to pretend like we're reversing the entire track. In other words, since we reverse both cars, it'll still work out just right. It's a very good question. Just to save us some time, we won't have to change the sign. And so what you need to model is I want both of of them to be moving toward each other, and then both of them bounce off of each other. Don't send them too fast. I don't want you to smash them into each other, but definitely just... Oh, that was maybe a little too hard.
There we go.
Okay, that's a little too hard too. You'll figure it out. So somewhat slow. And last time, if you calculated previously, you will draw. If you drew previously, you will calculate. One more practice round before we take our break. Let's go. All right. So let me get your attention real quick. I would like to debrief about this warm-up activity, and then we'll take our break. So can I please have your attention just for a moment? This was an elastic collision, which means that both energy are conserved and momentum are conserved. When objects bounce off of each other, we consider it an elastic collision. But in reality, no collision in the entire world is ever perfectly elastic. Even the tiniest objects bouncing off, like a bouncy ball, is never even a perfectly elastic collision. But we should have found that our energies are relatively close. I think this group has some pretty good numbers, 0.056 and 0.056. That's pretty. You didn't fudge those numbers, did you?
No, I just rechecked them all too because we screwed up a little bit.
Good, okay. Their momentums you'll see are 0.23 and 0.23, and the diagrams we can use to also visually represent this. So I hope you found this warm-up activity to be pretty useful. We're going to take our break now, and we will do the notebook entry in just a moment. It's 3:27 right now, so let's take a break, and I'll see you at 3:33. All right. So... So, today's lab is called Momentum Mayhem, because we got a demolition derby going on with our cars. Momentum Mayhem. And we are going to explore the idea of impulse. Impulse is this quantity that talks about the change in an object's momentum based on a force that acts over some time. This right here is what we call impulse. And we can all be a little impulsive sometimes, can't we? Me more than others. So, given this equation that we'll be exploring today and thinking about what you can get from Capstone and the smart car, can someone please help me list out what variables we might need? There's 4 that I'm looking for from that equation. Jason?
Mass.
Mass is one of them. What is the symbol for mass?
M.
That's right. And what units do we use?
Kilogram.
Correct. Who's got another one, August?
Velocity.
Velocity is one that we will be able to get, even though it doesn't show up quite in that equation. It is hidden away somewhere. August, what's the symbol for velocity?
V.
Good. And what is the units?
Meters per second.
Very nice. Who thinks there's some other variables? Sam?
Time.
Time is another one that we could get from Capstone. Symbol? What symbol is it, Sam?
Oh, T.
Good.
Sorry.
Little t. And what units does it have?
Seconds.
Good. And Lillian's got one more.
Force.
Force. We can also measure because we have a force sensor on this. Symbol?
Newton.
That is not the symbol that we put in a math equation.
Symbol is F.
Good. Yes, capital F. And the units are newtons. Very nice. I saw your hand up, but sorry I didn't call on you. And for our problem statement, how does blank depend on blank? We're actually going to ask the question, how does impulse depend on the change in velocity? Change in velocity. Okay? And so there will be something that will remain constant. First, let me show you what the experiment will look like, and then I'll ask you to reflect on what you think will be constant. We are basically going to send this car with the magnetic bumper facing this other magnetic bumper at the end of the track. And so it's going to have a momentum coming in, and then when it bounces off, it will have a momentum coming out. In other words, its momentum will change. Like that. That's the basic experiment. Right? And we'll try varying it up so that it goes in slow, maybe medium, and then fast. So, thinking about that experiment, what is something that you think will be constant for all of these variables? Mara?
Mass.
The mass will be constant, and we'll need to figure that out. Mass of the car will be constant. Let's go ahead and measure that real quick. Give me a sec. So go ahead and measure the mass of your car.
0.776 kilograms.
That's what the way.
Let's use the line, okay.
It should be 0.2. Or 0.2.
Kilogram?
Yes.
Make sure that you have it in kilograms, please. So, Jason, you had another thought. I don't mean to ignore you. What was your hand raised for?
The force produced by the magnet.
Okay, so let's actually explore that. So the force produced by the magnet. I like that we're talking about this. You're saying it's going to be constant.
What I mean is like how, yeah, sure.
Right. Okay, and we're going to explore 5 different collisions for this car. One where it's going in slow, and so this bumper exerts a force against the car, and then another one where it's going in medium, and another where it's going in fast. Do you think the force that was exerted on that by that bumper will be constant?
Like exerting onto the car.
Yeah.
Yeah.
Okay, it actually will not be.
Oh, great.
The faster that it comes in, the harder the force is that is exerted to change its momentum. I'm glad that we're reflecting on it and thinking about it. What I mean is when it goes in slow, the force that it had to exert was kind of small. But then the force that if it's coming in fast, I'll go even faster. That force will actually be even bigger to change the direction of that momentum. So it's a good idea. Your head's in the right place. There actually is nothing else that will be constant that I would like to list for this one. Of course, we could talk about gravity, but in this experiment, gravity actually isn't all that relevant. But there is one other thing. We won't have any different initial conditions, but we will have some precautions here. And I want to make sure, yeah, you basically have it. I want to make sure, do not let the car crash too hard. In other words, I do not want you to send the car in so fast that it actually hits the bumper. I don't want you to do that. Don't be like me. I mean, be like me, but don't be like me that I just demonstrated there. So, I am not going to show you how to sketch your experimental setup. I've given you hints last time. It was really easy to grade. This time I'm not going to super handhold, but I do want to list that you need to have all 4 of those variables that we have up top in here. In other words, you will need the force applied by the bumper onto the car. You'll have to put somewhere where that force exists as an arrow. You will need the velocity of the car. You will need the mass of the car to be listed. And you will need to list where we get time from. It's from the computer. Okay, so you'll need a track, a bumper, a car, and a computer drawn on here with where all the variables show up. I'll let you work through that in a moment. Since our problem statement is how does impulse depend on the change in momentum, let's put impulse on the vertical axis for our prediction. It's delta P. And the units that we actually have for impulse, there's 2 different answers, but the ones that I want are the units of force times time. In other words, the units will be newtons times seconds. N times S. You might recall from the PowerPoint that the area under that graph had units of newtons times seconds because we had force versus time graph. That's what I mentioned at the beginning of class. That's in the PowerPoint. The horizontal axis will have delta V, which is going to be a change in meters per second. I'll let you do your prediction in a moment. Follow along with me. Your independent axis will be delta V in meters per second. Your dependent axis will be delta P in newtons times seconds. And so we're going to get 5 different runs where you send it in super slow, kind of slow, medium, kind of fast, and super fast, but not letting it actually hit that bumper. So, before we get started and continue onward, let's have each person currently on the computer wiggle the mouse. We got 3 weeks with these groups, so everyone will get a chance to be on the computer, but for this week, just let somebody be it. Is there an issue?
Yeah, there is.
Nate, can I have you give it a shot? Maybe do some plug work. Nate is our tech expert, so we'll see if he can figure it out. It worked last class, so I would be surprised if it didn't work this class. All right. please go into Capstone. Please turn on your car and get hooked up with your sensor data. And also, for anybody who's not on the computer right now, please carefully pay attention to these steps, which will of course be posted on YouTube, but we're getting closer to thinking about the end of the semester where you will have a lab practical, and the lab practical very likely will rely on you knowing how to do Capstone on your own. Nate won't be here, I won't be here. So you will have to know how to do the following steps. We've been doing this a lot lately, so please just follow along with me. First, what I want to do, let's close our hardware panel. We'll go back in there in just a sec. But let's go down to the bottom. Get to your smart car position sensor. I'm already on mine. And make sure that you hit the 0 sensor now button. You want to make sure it's zeroed so that it reads 0 when we're not moving when we're at 0. Also, we are going to use the force sensor to measure force in this. So please go down to the bottom. Click on your smart car force sensor. And in the smart car force sensor at the bottom, make sure that you also 0 the force sensor. You should now have your position sensor and force sensor zeroed. And then at the bottom, last thing is we want to go to common rate to make sure that it collects both of those data at the same rate. When you're in common rate down at the bottom, the last thing that you need to do is it's collecting 20 samples every second. Since this collision actually happens within a fraction of a second, not even half of a second, we want to collect as much data as we can. So up that number from 20 hertz to 100 hertz. Take 100 samples every second. Everyone should now have their position sensor zeroed, their force sensor zeroed. They should have the common rate selected and set to be at 100 hertz down at the bottom. Another thing that we're going to need to do is in the hardware setup, let's open up that panel again. And it will actually be more convenient for this experiment if we make sure to change the sign of both our position sensor and our force sensor. So go into your position sensor properties and click change sign. If you had it checked, you are good to hit OK. In the smart car force sensor menu, do the same thing. So go to the properties of the force sensor and hit change sign. And then hit OK. You can close the hardware setup panel. We should now have everything zeroed, everything collecting at a common rate of 100, and the sign changed for both of these. We will need to add a new plot area. So we want to have 2 plots here, so make sure that you hit that little axis with the yellow window, adding a new plot area to the graph display. And on the top graph, I want to have velocity from your smart car position sensor. And in the bottom graph, I want you to have force from your smart car force sensor. I'll get a little bit of room here by getting that out of the way. And so let me show you one of these collisions, and let's just talk about it for a sec, and then I will show you how to do the entire experiment, and I'll let you get rolling. We're going to hit record. It's going to start recording. We're going to send this car in, and we get a little blip in our force versus time graph, and we get a change in velocity. This was my velocity that I had coming in. This is my velocity that I had going out, much like what we just did. Of course, the collision actually happens right here at that time, and you can see that a force was exerted. It was felt by the car. And we're going to learn a new technique here. So before I show you the new technique, I am going to just show you for this calculating the change in velocity. What you will want to do is you will want to figure out what your initial velocity was, like right before the collision. So maybe I'll even just zoom in a little bit so everybody can see. Maybe I'll just go from 4 to 6 seconds. Just so that we can see here for this particular example. Okay. You can see that my initial velocity that I had, make sure that you don't select anything in this region where it's starting to change its velocity. You want to like over select a little bit, so make sure that you select a point that's like well before the collision. We can see that I'm coming in with a velocity of an initial velocity of negative 0.418 meters per second. We will see what my velocity was after the collision. So you don't want to select way over here, because you can sort of notice that it is going down over time. Friction is acting. So we kind of want to pick like right after the force was exerted, but not too far over. There's sort of a delicate balance of knowing where to select. So you'll want to pick maybe a velocity right around here. And I left with a velocity of 0.402 meters per second. If you needed to calculate a change in velocity, we do final minus initial. I'll have a 0.4 minus a negative 0.4. For this example, for this data point, my change in velocity was like 0.82 or something like that. Positive number minus a negative number should give you a positive value for the change in velocity. And now I would like to show you how to do this. Nate and I will probably have to rotate around at some point. We need to figure out the area under this force versus time blip right here. We need to figure out what the area is of that, because that will tell us the impulse in newtons times seconds. There's a special tool that we haven't used yet in this class, and it's going to be this area under the highlighted data. But before we do that, we need to actually tell it which spot we're looking at. So I'm going to use the highlighter window, and I am going to make sure to select everything where that blip occurs. Make it a little bit bigger. Okay, there we go, good, nice. Just give me a sec, I got this. Get this out of the way. Come on now. Good, there we go. I want to make sure I highlight the entire blip itself. And then once you have a highlighted window where you see the force occurring over time, you will go to this display area under the highlighted data, and you can see that it gives us the area underneath that within that region. It's 0.2 newtons times seconds. That's the value that I would have for my delta P. So we've calculated our delta V by using final minus initial, and we've determined our area under the curve to get our impulse using that new highlighter plus area tool. Now, this, you don't actually have to do it one run at a time. So what we're actually going to do is try doing it all 5 runs in the same time, and then you'll just carry out the data analysis and the computer work. So I'll just demonstrate for you what I mean. What you'll want to do is you will want to send it in very slow, a little bit faster, a little bit faster. Oh gosh. There we go, even faster. And maybe one more really fast one. You can see here that I have, let me get this area out of the way. You can see here that I have 5 collisions. 1, 2, 3, 4, 5 in increasing size. Maybe these two aren't quite all that different. And you can see that in the velocity graph I have 1, 2, 3, 4, 5 collisions, each with their final and initial velocities that we would extract using the coordinate tool. And so you'll be able to calculate 5 different delta V values. You will be able to use the area under the curve to determine 5 different delta P values to go along with that. And then we'll plot it in Excel and follow the same steps that we always follow to determine if we need to linearize it, and get out the slope, specific math model, and we'll see where we end up getting. Any questions so far? All right, then let's go ahead and try to do it. Once you have this run, you can call Nate and I over and we'll say, looks pretty good. Try to get a good variety of different forces, so really don't be afraid to start too slow with the really slow one, and then slowly increase your speed for each collision. And I wish you good luck in this. Talk to you soon. Also, please, before you get started any farther, make sure you make a prediction. Please talk to your group about what your prediction is. Make that prediction now. All right, I think it's about time for us to go through this. So, may I please have your attention? And let's take a look at the notebook entry. I have some sample data here that I will be providing for some people who are not able to attend today. On your raw graph, you should have delta P on the vertical axis. It should be positive. It's in newtons times seconds. And you should have delta V on the horizontal axis in meters per second. And you should have had something that looked somewhat linear. We did not need to linearize this one. Don't forget to include your numbers for your actual experiment there on the tick marks. Didn't need to linearize, so we can skip that. Let's take a look at the back page. We needed delta P in newtons times seconds here, and delta V in meters per second. And do not forget to draw whatever your trend was. This time it was a straight line. My slope that I get for mine is 0.2476. 0.2476. And it's got units with the rise over the run. That is newtons times seconds. Newtons over meters per second. But wait, there's a way that we can simplify those units by thinking about the units that are hidden away inside of a newton. Inside of a newton, since newtons are determined to be the unit for force, and force, your physics tattoo, is F equals ma, we should have newtons which actually have units of kilograms times meter per second squared hidden away inside of them. And if we were to do some simplification now, we would have on top here for our slope, instead of newtons, we'll put kilograms times meter per second squared. We need to tag along that seconds that was still there in our impulse, and meters per second on bottom. So one of these seconds will cancel that squared out, and now I have kilograms times meter per second over meter per second. That means that I can cancel those meters per second there, and what I'm actually left with for the units of my slope are kilograms. That should already be a little bit of a giveaway about what the slope is actually related to, but I'm just going to continue on. My intercept is 0.0003, 0.0003, and the units should be newtons times seconds. You should include a number here from your data table for all of those, and you should have your percent calculated for the 5% rule. Let's just get a quick read. Who had above 5%? Not a problem. Who had below 5%? Great. Okay. We're going to assume that everybody had below 5%, so just make sure you fill in your 5% rule calculation, and you'll get a check mark there. For the specific math model, we have delta P on the vertical axis is equal to whatever our slope is, minus 0.2476, and we already figured out that the units are actually just kilograms. My delta V tags along as the independent variable, and I have 0.0003 newton seconds as my intercept. I wonder if there was a negative there. There was a negative, so I better make sure to carefully put that negative in there. -0, negative, good. And we are going to have everybody just assume that this intercept goes away. It's not important, it's negligible. A little bit of errors came up in our calculations, and we'll talk about where that intercept came from. For our generic math model, we drop down the dependent variable. We have a slope. I'm just going to call it k for just a moment. And our independent variable is delta v. If you did have a residual intercept in there, you could have put some kind of delta p0, but for right now, I don't want anybody to have that on their sheet of paper. Let's just cross that off. That doesn't need to be there. And this slope k is actually related to something about our experiment that's constant. Since our slope was constant, Ariel, thank you, m. And so the slope is related to our mass. So the mass of your car should have been somewhere around 0.27. My slope that I got was 0.25. Can I just get a quick read on what your slope ended up being over here?
It was 0.2427.
0.24?
0.271.
0.271. That's pretty darn close.
0.25 and
0.25.
0.267.
0.26. That's pretty darn close too.
0.251.
0.25.
0.25.
0.25. 0.3.
0.25.
0.25. Pretty darn close to the mass of your car. So that's what we were hoping to get there. Mine is 0.25, and I was off by a little bit, but that's okay. Our numbers aren't quite perfect. So the meaning of the slope, there's two things that you could put here. I'll give you the long explanation, and then we'll try the short explanation. You can say, for every 1 meter per second change in velocity, an impulse of 0.2476 Newton seconds was delivered to the car. You don't necessarily need to erase what you have. I'm sure what you had is probably fine. So that's really what we have here. We have a change in our velocity of 1 meter per second. That's what's on bottom. And that means that we had an impulse of 0.25-ish Newton seconds that was delivered. Or I would totally accept your meaning of your slope, just saying the slope is the mass of our car. Something in the ballpark of that means that you got it figured out. Meaning of the intercept. Let's all make sure that we have something similar here. The intercept should be 0. But there might be some errors. Because this collision might lose some momentum somewhere else. Might lose some momentum elsewhere. And really, if you did have a 5% rule that said your intercept was meaningful, let's take a quick sec to think about this actual experiment. This experiment assumes that the track is... It assumes that it's frictionless, right? So we could have some losses due to friction. Totally viable. It also assumes that the track is fixed in place. That means that all of the momentum that this thing came out with, we're saying it's an elastic collision and it's leaving with the same amount of momentum that it started with. But this bounce is not perfect. Some energy is lost in this collision, so it's not a perfectly elastic collision. It might be a little bit inelastic, but also there's something else that we're assuming. We're assuming that this track doesn't move at all in the collision. And maybe when we go slow, the track doesn't move at all. But you can almost even see it in my little loose bumper here, that when I send it in, it does push on it a little bit. It's not perfectly fixed in place. And I think it'll be even more obvious if I really do a fast collision right here. So watch the track, watch the bumper, and ask yourself, does the bumper and the track really not gain any momentum at all? Did it look like that track stayed fixed in place? We'll try again. We'll try again. And eventually, my track would end up falling off the table if I did this long enough. This track does get bumped a little bit. It does gain some momentum. This is not just all of the momentum that's coming in being transferred back out to that car. So there's a little bit of sources of experimental error here. Your bumper might wiggle a little bit, there might be friction in the track, there might be some sound that's being generated and losing energy. This track might bump a little bit. And all of those could be reasons why we have some error in this experiment. Mara?
I just had a question about your meaning of the slope, your units. Why is that newtons times seconds, not kilograms?
Well, I am looking back at what we have written up here. This is a good question. Originally, I'm sure most of you had this written, right? And then you maybe changed it to kilograms. We can view it from two different lenses. You can either say that the slope is the mass of your car. And in that case, the slope is kilograms, right? That's this bottom sentence here. The slope is the mass of our car measured in kilograms. But when I think about it from this top perspective, if you look at this and think about the rise over the run like we've done for all of our slopes up to this point, we always say for every change in the independent variable, for every meter per second change in velocity, we expect to see a change in the dependent variable, a rise of 0.2476 newtons times seconds. So really this first meaning of the slope is following the form that you're given in your notes. For every change in 1 unit of the independent variable, we observe a change in the dependent variable equal to the slope value. So this bottom part is a shortcut. The top part is the true official way that we've been doing it always up to this point. So that's a really nice question. I just wrote it out more specifically, thinking about this thing in the bottom and the thing that's in the top for that slope. Let me take a look at my time, 4:39, nice. So for the last diagrammatic model, we have momentum diagrams. Let's make a couple of notes before we draw the momentum diagram for this situation. 1, draw a vertical axis to represent velocity. And horizontal axis to represent mass. 2, draw a rectangle to represent the momentum of each object. In the third step, calculate the area of the rectangle to solve for momentum before and after collision. We've gained a lot of practice doing that. Here we go. Make that a little bigger for you. And I'm going to go ahead and draw out my momentum diagrams now for this one. So I want to get some axes there. There we go. Looks pretty good. And then I will draw some more axes over here. Come on, everybody, get there, get there. Nice. Good. Maybe I'll do a little bit of erasing. We've gained a lot of practice doing this, so we're going to draw the momentum diagram for just the car. This on the left will be our initial situation. This on the right will be our final situation. And my car has a mass m equal to 0.275 kilograms. And it had a velocity that I'll just call v initial. I should be able to draw a rectangle there. We're only doing it for one object on this one. And the area of that rectangle is P1 initial, m times V1 initial. It should be negative, I'm just now realizing. So, sorry about that. Let's do some quick fixes here. I'm going to make that rectangle go in the negative. Initially, our velocities were negative for all of these. There we go. Maybe I'll grab this. Move it up a little bit. There we go. I'm going to draw my rectangle in the negative because we had an initial negative velocity. Just doing a relative drawing right now. V1 initial. And so the momentum of this first object initially should be m1 times v1 initial. And in the end, it had a positive velocity. So I will draw that same width of rectangle, and it had just about the same velocity on its way out that it had going in, but in the opposite direction. Here I got m1 still 0.275 kilograms. P1 final would be the area of this second rectangle, V1 final. So here we have a momentum diagram for an object that had an initial negative velocity. Its final velocity was positive. V1 final ended up being positive there. This is a good example of our momentum diagram, but there should be something that you notice about this that is different than any momentum diagram that we've drawn up to this point. They know what I'm getting at. Zoe?
There's only one object.
There's only one object, that's for sure true. It's not quite what I'm looking for, but you're right. We've been doing two-body collisions here. Lillian?
There's no actual values.
Okay, there's no actual values. Good. What if I add up the area of the initial and compare it to the area of the final? Tyler?
Should be equal.
They should be equal. Are they equal in this case? This one's got a negative area. This one's got a positive area. It should be equal because momentum is conserved in every collision. But there actually is a little tiny tagline after that. We say momentum is conserved for every collision. ... Does anybody know what it said it in the PowerPoint? Does anybody know what I'm getting at? Lillian.
In a closed system.
It's in a closed system, and this is not a closed system. We didn't include all of the objects that matter in our system. We could have thought about the momentum of the car and the momentum of the track, and as we already sort of spoke about, that track does gain some momentum afterward, and it's honestly got a lot more mass than the little red car, so we would have to have another blue box for the track itself with the bumper attached. But since we only chose to draw one object here, this system is not a closed system. It's not an isolated system. There are external forces coming into what we've chosen to draw. There's external forces acting on the car. That is the force that we actually measured. So let's make a little note here. In this case, momentum is not conserved because this is not an isolated system, or the book calls it isolated. We've been calling them closed. This is not an isolated or closed system. The bumper exerts an external force on the car. So if you have external forces coming in from things outside of your system, then momentum will not be conserved, and that is why we have a difference in the initial momentum and the final momentum. The totals are not equal. One of them is negative and one of them is positive. Okay, that is all that we'll end up doing for class today. This is available to be posted on Gradescope, so you can just stick around in office hours and take a pic right now and get your deliverable turned in. Could I please have you close everything on your computer and not save it? Could I please have you take down your whiteboards, erase them, and return them? And thank you very much for your diligence. Great job working all the way through the class period, and I will see you on Friday.